Hi, I'm Mark Coletti. I'm a staff scientist at the Oak Ridge National Laboratory. And today I'm going to talk to you about diagnosing autonomous vehicle driving criteria with an adversarial evolutionary algorithm. So the first thing I want to focus on is that we are trying to develop a convolutional neural network to drive an autonomous vehicle in a virtual environment, which you can see a screenshot here. This is from the Carla virtual environment, which is an open source environment specifically designed for facilitating the training of models for autonomous vehicles. And one of the things that we're struggling with is the fitness criteria of how to measure the behavior of the autonomous vehicle. One of the problems that we encounter in legacy approaches is that they don't do a very good job of measuring the quality of driving. So that's one of the things that we wanted to concentrate on is, can we measure how well it stays on the road, how quickly it comes to a stop and starts, and those sorts of things that weren't actually adequately covered in previous work. So what we were to use was something called Gremlin and Mendel. So the original intent for Gremlin was to be an adversary for Mendel. Mendel is another evolutionary algorithm that was going to take training data, which is shown in this, represented by this icon here, to train a convolutional neural network. The output is shown here. And Gremlin was going to take that model and drive it around thousands and thousands of times to try and figure out where the weak areas were, or where what particular scenarios this model didn't perform well in. And the idea was to go back and adjust the training data to include more examples of those poor performing scenarios and just repeat the training process all over again. So while we were working on Gremlin, we noticed something very curious. So when we started out developing Gremlin, we didn't have any models yet to test Gremlin against. So what we did is we took what's called a Carla roaming agent. This is a perfect driving robot that drives around this virtual environment. And we're using that to actually take regular snapshots of the environment that we would use for training data. But what we were using then was this roaming agent as a proxy for the model, so that we can have Gremlin just use this roaming agent just to exercise the code to make sure that it was running fine. When we did this, we noticed something very, very curious. I'm going to bring your attention to this plot here, the scatter plot. So in town 1 for Carla, we had overlapping segments that are numbers. So this x-axis is basically the specific ID of a particular part of a road in town 1. And we would expect for the roaming agent, since it's a perfect driver, is that it would get 100, which is the best score, clear across the board. These blue dots show areas in the town where it was not getting a perfect score. This is something we weren't expecting. So the next thing we did is like, well, let's see where this is happening. So these are just parts of that town, and these blue dots represent areas where the roaming agent did well, as expected, but the red are areas where it didn't do well. So we noticed a pattern, and that pattern was it wasn't doing well on turns. So we figured out the problem was that Gremlin had discovered by accident was that the fitness evaluation criteria we were using was broken in some way. And how was it broken? Then we needed to adjust how the waypoints were being handled for doing turns. So once we made those corrections, to go back up here, the red shows that we had a marked improvement in the roaming agent. And actually, since these results were done several months ago, we've actually improved this even further. So what we found by accident is that Gremlin had a secondary purpose, that it could also be used to kind of troubleshoot our fitness criteria. And we've been using it in that way ever since, as sort of a regular standard check anytime we make a change to the fitness criteria or using the evaluate autonomous vehicle behavior. So that's our work in a nutshell. We did this on the Summit Supercomputer at ORNL. If you have any questions, here are our email addresses. Feel free to reach out to us. I hope you enjoyed this very short talk and our poster. So thank you very much.